We are now encountering springs, which back in chapter 5 we first introduced the idea of the spring force, but now we are actually going to calculate it and do something in detail. The caveat being that later in chapter 10 we're going to meet the potential energy of a spring, so this is only part of the story right now. We're going to start with forces. So when we're talking about a spring, the first thing that you must know about a spring is what its equilibrium length is. This is its unstretched length. How long is it when it is just sitting there? Now, if you imagine a situation like a rubber band, that is an object that can stretch but can't really compress. If you imagine a slinky, it is also a spring that starts really compressed and actually can stretch, but can't really compress based on its equilibrium position. So in physics class, we're usually thinking about an object that can both compress and stretch, but elastic objects, like a rubber band, we're going to model as a spring, but it doesn't necessarily make sense to think about them compressing. So the spring model is very much a model. We are taking a real-world object and we are going to simplify it enough that we can actually do some calculations with it. So whenever we're dealing with springs or elastic objects such as rubber bands, we're assuming that they are ideal. Now part of that is that they're massless so that we don't have to worry about the motion of the spring itself. And we're going to be able to talk about our object based on one number, the spring constant K. And this is a lowercase k to differentiate it from kinetic energy, which is capital K. Most of us, when we actually write K, it looks the same if it's uppercase or lowercase. And that's one reason why I typically write KE for kinetic energy rather than just K. So you might want to be careful and try to find a way to make your lowercase and uppercase Ks look different, since we frequently use these at the same time. So the equation that we're going to be dealing with for forces gets called Hooke's law, and ideal springs obeys this, but I want to highlight that this is not actually a law. Newton's second law is a law. Every object in the universe obeys Newton's second law. Hooke's law is a simplification and kind of a rule of thumb. It is a model we are using, but it's not really a law. The idea is that the spring force in direction S, where again this could be X or Y or some general direction, is negative the spring constant K times delta S. And this delta S has a very specific meaning here. This is how the spring length has been changed from the unstretched or equilibrium length. So this is important to think through. If we have a positive delta S, that corresponds to our spring being stretched. If we have a negative delta S, that corresponds to our spring being compressed. So let's think about this coordinate system up here. The direction to the right is positive. So if our delta S is positive and we look at this equation, K is a positive number. So the spring constant is always a positive number. It has units of newtons per meter. But then there's this minus sign that tells you the force, the spring force, the force that the spring is exerting on the object, is negative. So the spring force, which is in red, is to the left. It is negative. But the delta S, the displacement from equilibrium, is positive. Vice versa, if we look at the next situation, our spring is actually compressed to the left, so delta S is negative, right? The left direction is the negative direction. But that means, with that minus sign, that the force is to the right. So the force is always pushing you back towards equilibrium. If you've moved to the left from equilibrium, or the unstretched length, the force then pushes you back to the right. So what that looks like if we plot it is that right at delta S equals 0, right at your equilibrium position, there is no force. The spring is happy to sit there, no force is exerted. As we move to the right, you have a negative force because that's pushing it back to the left. And if you actually have a delta S to the left, you have a positive force, which is pushing it to the right. So be careful in that this force plot can be a little confusing, but this is just a different way of representing what we've shown up here with arrows. So again, these directions are really important, and it's tricky to remember here that when we talk about delta S, we don't necessarily mean final minus initial. So normally when we mean delta, when we say delta, we mean final minus initial, but here we are always talking about displacement from equilibrium. So you can actually relate this to other things going on. So for instance, you might be told what the position is from the wall. And so little L1 and little L2 might be the distance from the wall. You can't just plug that L into your spring force equation. That would be incorrect. But if you know what the equilibrium position of your spring is here in green, you would actually subtract your equilibrium position from the position it's at to again get a negative value if it's to the left and a positive value if it's to the right. So be very careful about what length goes in. Remember that it is the displacement from equilibrium. And again, left versus right is going to give you a sign that's important for this force. However, you should also be able to always double check that your force directions make sense. So make sure you're defining the positive direction in this coordinate system.